So here we'll take a look at a few more examples of finding that first derivative using the difference quotient, using the limit as h approaches 0 of that difference quotient. So the idea being the first derivative is the limit as h approaches 0 of our slope fraction, called the difference quotient. F of x plus h minus f of x, so the difference between the y coordinates, over the difference between the x coordinates. So we saw how this worked for f of x equals x squared. So now our function is a linear function. F of x equals negative 4x plus 3. And so we know that the slope of the line of a linear function is constant. It never changes. And that slope is, in this case, negative 4. So we should, when we're done, get an answer of the first derivative formula being negative 4, meaning that no matter what value of x we're at, the slope of the line is, the instantaneous slope of the line is negative 4. So let's see if that works here. So again, I'm going to take this statement right here, and now I'm just going to apply it to this specific function. So we're going to have our first derivative is equal to the limit as h approaches 0 of, now f of x plus h just means that I'm going to take my actual function formula here and replace x with x plus h, just like we did with the previous example in the previous video. So we're going to have negative 4 times x plus h plus 3, and then minus, now we have got to subtract f of x, which is going to be this original function, negative 4x plus 3. And so just note that it's really important that we put that in a set of parentheses because we're subtracting the entire expression. And so if we don't put the parentheses, we'll lose the distribution of the negative sign, which will throw our answer off. Now for the denominator, it is always going to be the same, x plus h minus x. Because again, the idea is we've got these 2 points that could be located anywhere along our curve. One is at xf of x. The second one, I know it should be going down instead of up, but you get the idea. One is at x f of x. One is at x plus h f of x plus h. And we're trying to find the slope of the line that goes through those 2 points, but we're eventually narrowing down our gap between the 2 points, this horizontal distance between the 2 points h, we're narrowing it down to 0. So that's what this statement is saying. We're finding the slope of the line, but we're going to shrink the gap between the 2 points down to nothing. So in my numerator, I'm going to kind of clean house a little bit, do a little distributing in this first piece. So I'm going to get negative 4x and then negative 4h. And I still have the plus 3. And then I'm going to distribute this negative over here. So I'm going to get minus a negative 4x. That's going to become plus 4x and then minus 3. And once again, just like we did in the previous example, when we simplified the denominator, we're going to end up with just h. The x's subtract out, and we're left with just h. So before I can plug in h equals 0, I still have to remove my discontinuity. So before I do that, I need to kind of gather like terms up in the numerator of my expression. So hopefully we can see that the negative 4x's cancel out, and the 3's cancel out. So out of all of that on the top, we're left with negative 4h, and in the bottom, we're left with h. I still can't plug in 0 for h. I'll end up with that 0 over 0, but we can see that now the h's are going to reduce away, and so now my simplified expression is just negative 4. And so now I can go ahead and apply my limit. I can set h equal to 0, which is pretty easy in this case because there's no h to replace with 0. So I now have my first derivative is negative 4. And so this confirms what we kind of predicted at the outset here, is that for a linear function, the slope is going to be constant. So no matter what value of x we plug in, at that location, the slope of the line is going to be -4. And that's exactly what we got. So we'll step up the difficulty level a little bit here with a function that's not linear. So we're not going to have a constant value for the first derivative. It's going to be varying depending on where along the curve of the parabola we are. And indeed, we have a parabola looking at our original function. And it's got a little bit more going on than just our original function that we looked at, that f of x equals x squared. So I've got the formula, the limit expression to the, applied to the difference quotient that we're going to use here specific to our function. So I'm going to get ourselves started here. So the first derivative is equal to the limit as h approaches 0 of, and so now my first part of the expression is going to be f of x plus h. So that means in this function right here, everywhere where I see an x, I need to replace it with x plus h. So I'm going to have x plus h squared minus 4 times x plus h, and then minus 12. So that there is my f of x plus h. I've just plugged in x plus h into my function. And then I'm supposed to subtract f of x. So I'm going to subtract just the original function as it's written there, x squared minus 4x minus 12. So that is my numerator. My denominator, same as it ever was. Difference between the x coordinates of my 2 points, so x plus h minus x. So now I just have a whole lot of housekeeping that I've got to do up in the numerator. So I've got my limit. Again, you have to write this every single time because it's part of the expression. So I need to FOIL this x plus h squared. We've done that previously. So that's x squared plus 2xh plus h squared. I now need to distribute this -4 right here. So we get -4x minus 4h. And then I still have the minus 12. So that's now the expanded expression for the first part of the numerator. And then I still have minus, and I'm going to go ahead and distribute the negative here to everything. So it's going to be minus x squared plus 4x and then plus 12. So we've got the numerator all expanded out. In the denominator, x plus h minus x simplifies into h. So we've got our limit as h approaches 0 of, so now we can do our combining of like terms in the numerator. Got x squared minus x squared, gone. We've got a -4x and a positive 4x are gone. We've got a -12 and a positive 12 also cancel out. So everything that's left in the numerator, we've got 2xh plus h squared and then minus 4h. That's all we have left up top. And then we still have the h in the denominator. And so hopefully we're starting to see a trend here that once we've kind of cleaned up the numerator, every single time, everything in the numerator has to still have an h in it. If it doesn't have an h in it, then we're not going to be able to do the next step, which is remove the discontinuity, which is what we're going to do here. Because if I can't divide out the h's, then I'm never going to be able to set h equal to 0 because I'm always going to still have 0 in the denominator. And so we can see that the h's cancel out here. We're left with just h there, and the h cancels out there. So now we've got 2x plus h minus 4. And so now we no longer have an h in the denominator. We can go ahead and apply our limit. We can set h equal to 0. And so when we do that, we get 2x minus 4. And so here is the formula for our first derivative of this function, f of x equals x squared minus 4x minus 12. And so it's into that formula. If I wanted to know what's the slope of the line tangent to that parabola up top there at -3, I could go ahead and plug in -3 into my function. And so then I'd get 2 times -3 minus 4. And so we'd end up with -10 as the slope of the line tangent to that curve.